We're going to look at another nucleophilic addition. This time we'll look at another named reaction. In this case, this is the Wittig. We're looking for a carbon nucleophile. So what we want to do is address kind of the basics of the pieces behind what's going on here. So to start off with, we are saying that it is a carbon nucleophile. So if we go through and look at our starting carbons, bromine is more electronegative than carbon, which means that carbon would be positive. That looks pretty electrophilic. If we look at our next carbon source, that carbon with the oxygen being more electronegative would suggest that that one is electrophilic. So this is getting problematic, but we have one more carbon source that was kind of indirectly named with our butyl lithium. And if we were to draw that out, we have lithium connected to 4 carbons. And we might say, well, there's our nucleophile because carbon is more electronegative than the lithium. However, if that was the case, we would have expected the butyl lithium to appear in our product, and it does not. If we look, our starting alkyl halide is a 3-carbon chain. Here's a 3-carbon chain. And then our starting ketone is right here. So that apparent negative carbon ends up not being a nucleophile, and we are somehow connecting the electrophile of a ketone and the electrophile of the halide. That doesn't really seem to jive with our understandings behind this. Okay? It is a multi-step reaction, so there must be something going on in this multi-step process that is allowing that kind of change in charge so that we can get those two things to connect. And yes, it is a very advanced reaction, but it does some really cool stuff, and that's one of the reasons why it gets named. Okay? So let's break it down into each of those individual steps and see if that can help us kind of figure it out. So as we're going through and looking at this, we need to ask ourselves for each thing, what are the potential reactive sites? So if we look at step 1, okay, we're taking that alkyl halide with the phenyl or triphenyl phosphorus compound. They're somehow doing a reaction. The product of that then gets reacted with butyl lithium. The product of that then gets reacted with the ketone to make that final connection. So as we move through, we want to break this into parts and think nucleophile, electrophile, all the way through, or potentially even acid and base. And we want to address those pieces. So let's go ahead and start it off with the simplest of them. If my technology would work for freaking once. And we're going to start forming this fancy thing called a Ylide, and we'll address what that is when it shows up. So first step, nucleophile, electrophile. So what is the most likely thing to happen here? And we want to address kind of the why. If we break down our individual pieces behind this, hopefully what we can see, starting with the easiest structure, would be that our carbon is going to be very partially positive and our bromine will be very partially negative, okay, because of the difference in electronegativity. If we go through and look at the next structure, first and foremost, this should scream steric hindrance. Okay, that is very massive with those phenyl groups, and that's going to make it a tricky molecule to work with. The next part is trying to address the chemistry behind it. We do have carbons connected to that phosphorus. Phosphorus is more electronegative, so we might expect a partial negative charge to build on that phosphorus and those carbons to be partially positive. Okay. Those carbons being sterically hindered are not likely to be potentially reactive, which means we're really zeroing in on that phosphorus being partially negative with that lone pair of electrons. Should it act as a base or as a nucleophile? Well, steric hindrance is going to limit nucleophilicity, but phosphorus isn't a particularly strong base either. So how could we go through and swing this? Well, let's take a look at the substrate that we would be reacting it with. Note the substrate that we're using here is a primary halide. Primary halides undergo substitution much more readily than they undergo elimination, as we learned in first semester OChem, which would suggest that while we don't really like the phosphorus's potential reactivities, really the only thing available to us is that nucleophilic substitution. The result being is that we would get a god-awful looking structure with our phosphorus connected and then the phenols, which we could abbreviate as pHs, connected on the outside. That phosphorus has now donated electrons. It should become formally positive. And we can kind of highlight that as a new characteristic because it's, well, new. And we could see that new connection of the bond. We'd see the bromide floating around as a counter ion. You should have already seen, based off of working through some of the smart work, that counter ion is rarely, if ever, shown. So be aware, sometimes you need to show it, sometimes you don't, and that's going to depend on the question. And what we've now done is pretty much the only thing that we could possibly do. The elimination doesn't really make sense because we have a primary halide, and to run an elimination or an E2 elimination, we would need a secondary or greater. So with that primary halide, we're really only seeing a SN2 type mechanism come out of this. Okay? Is this what we actually see? Yes. Yes, it is, which is kind of neat. So we have now predicted, based off the structural pieces, what could have happened here, and it does actually work for us. Okay, so some big conclusions that come out of this: because this is an SN2 mechanism, we expect primary alkyl halides to work the best. So if we're going to run a Wittig reaction, we really want to see the primary halide in our reaction. Secondary work, but they are significantly slower. Okay? The whole point of this first reaction is really to prime that carbon. Remember, we needed a nucleophilic carbon. Where we're starting with the alkyl halide is an electrophilic carbon, okay, due to that electronegativity difference. But if we look at our product of this first step, that phosphorus, now with a positive charge, doesn't really want to be positive. So it needs to somehow get electrons. Those electrons would need to come from a readily available source, and that's going to now set us up for the next step. That carbon could now potentially become negative to directly donate to that phosphorus. For those people worried about octets, remember, phosphorus is special because it's in the third row. It could exceed its octet, particularly if we were going to minimize charge. So, next step of the reaction is the official formation of the Ylide. Okay? In that case, what we're doing is reacting it with butyl lithium. If we look, there's two potential ways butyl lithium could react. Okay? Because if we look at that overall reaction, lithium being low in electronegativity in comparison to the carbon, we're going to generate a very negative carbon. In fact, that's an ionic bond, so more than likely we're having a formal negative charge on that carbon. Carbon can't stabilize electrons very well, which means it's not particularly stable. If we're going to look at the reactivity, nucleophile versus base, which of those is going to be more likely for a very unstable species? The base is going to be the best option, and that's because the base can react readily, or more readily, or easily, because it's reacting on the outside of the structure with the hydrogens. The nucleophile characteristics is a little bit slower because it has to get to the inside. If we have a stupidly reactive carbon, or a stupidly reactive negative in this case, it's probably going to act as a base preferentially. So we need something to stabilize that. Okay. Regardless, we could go through and push this out and see what we saw for either situation. We could have it act as a nucleophile, or we could have it act as a base. And I think I drew those in the opposite locations in comparison to those boxes, but we'll just see. So if we were to draw it out acting as a nucleophile, that carbon could potentially come in, backside attack, fix the phosphorus. Our result would be, there's our starting 3 carbons, here's that new bond, and then our butyl lithium with 1, 2, 3, 4. Remaining piece would be pH3. this doesn't seem like a particularly good reaction to run, okay? Why would this be a bad idea? Well, we literally just put the triphenyl phosphorus on the structure. Why did we put it on there if the very next step is just to remove it? Okay, nothing about that really makes sense as a logical flow. Okay, so you could critically evaluate what you're looking at to help you kind of parse together and decide whether that was a good or a bad decision. So pretty arguably, that is a bad decision if you were given those reagents. What would happen if instead it acted as a base? Well, we need to stabilize that phosphorus. There are two potential hydrogens we could react with. Okay. If we go after the blue hydrogen, we end up just doing an elimination reaction, okay, which again doesn't make sense. We're ejecting the phosphorus that we just put on. Why didn't we just do that from the beginning? It would have been a lot easier. Okay. The red hydrogen ends up being a little bit better, okay, and for a couple reasons. If we go through and do that, there's our triphenyl phosphorus with the negative charge on that carbon. Okay, we could do a resonance stabilization of that positive charge on our phosphorus. That resonance is what actually drives the potential for this reaction to occur. pH3. Okay, again, we are exceeding the octet, but again, phosphorus is allowed to do that. Okay, so that butyllithium is now probably going to act as a base for kind of two potential reasons. One, the logic of the reagents doesn't make sense if it didn't act as a base. And two, we can stabilize those structures better if we run it through as a base. The base makes more sense overall. Okay? Because all of that is messy, let's go ahead and clean it up and look at those potential options. Oh, look at that. I did actually draw it in the proper places. We do have that potential site for resonance. I don't remember if I drew it. And there we go. Again, if we go through and evaluate this, really what we said was that that top reaction doesn't make sense. So we can do a whole bunch of scribbles through that. And really what we're looking at is that bottom one. That bottom one, this structure is what is known as a ylide. Okay, and I wish I knew the definition of that a little bit better, but it's that negative carbon next to a positively charged atom. Okay, and that does show up fairly frequently in other situations. So they don't have to be phosphonium ylides, they can be sulfonium ylides, where you're using a sulfur. The chemistry changes a little bit. Don't stress a whole lot about that. Just recognize that that term can be used in other situations. But this species is now our nucleophilic carbon. That carbon is now negatively charged, and now it can act as a nucleophile. And that's the cool part. For those of you saying, but what about this structure? Doesn't that actually show that we don't have a nucleophile? Okay. Isn't it saying that we don't have a negative carbon? Yes and no. Okay. Yes, we seem to have neutralized that charge, but how efficiently did we neutralize that charge? You might say, well, but there's no charge. Those electrons must share with the phosphorus, and this becomes tricky. If we're going to look at this in everybody's favorite viewpoint, a Newman projection, where we have the blue dot being our carbon and the phosphorus in red, okay, what we're looking at is p orbital overlap. Okay? For the carbon, we're looking at a p orbital, in fact, a 2p orbital. For the phosphorus, we'd be looking at a 3p orbital. That 3p orbital is so much larger that the overlap between those orbitals isn't all that great, which means it's not a particularly strong double bond, and it's actually better to reference it in the ylide formation with the negative charge, or with our charges in the structure. Okay? That is kind of a nuanced thing, so don't stress if you don't quite grab that, but that's why we have molecular orbital theories. It helps us to explain and predict a lot of these things that we can see. Okay? So, we now have a carbon nucleophile. That resonance stabilization aids in the formation of the ylide. It doesn't formally show it as the double bond, we should be better showing it as the carbon nucleophile with the charges. Now we can go into our third step where we're actually launching into the nucleophilic addition-elimination. Sorry, nucleophilic addition. And elimination, actually, though technically a little bit weird. You'll note that we have multiple arrows there, and we have this statement of mechanism debate. Okay, and what's happening is that it turns out that this isn't super clear, and that when we go through and change the identity of these R groups on any of these pieces, the results change. Okay, which means there's a little bit of a debate of exactly how the mechanism runs, which means good for you, you don't have to know the mechanism. Okay, you just kind of have to know the end result of this. Okay, but we can address some of the pieces of what we might predict. We have that negative charge. We would expect that to attack our carbonyl. Okay, that's going to force a breaking of that pi bond, making a negative oxygen. Well, if we look at this, okay, or align this a little bit differently, let's redraw this structure down here. So I want it drawn in that fashion. Okay, hopefully we can see that. We could see the negative aligned to the positive of that carbonyl, negative there, right? And be like, well, here's that connection we just addressed. Well, that brings this oxygen and this phosphorus very close to each other. And it turns out they are close enough that they also make a connection. Again, the exact sequencing behind this is a little bit up for debate, so don't stress on it. What you do need to know is that we form this kind of mess of a structure, okay, this big four-membered ring. This should look kind of familiar. This should look like the borane ring structures that we've seen before in our electrophilic additions. Okay, it's a slightly different mechanism, but we're seeing that same result. This structure is unstable, okay, and what will end up happening is it's now going to kind of fall apart. The sequencing behind that falling apart is that our oxygen will end up stealing the electrons and sharing with the phosphorus. Phosphorus will then be like, well, heck, I got electrons, I don't need them. It can shuttle electrons here. The end result of that, you should hopefully be able to see, and I'll try and draw it where I haven't moved anything, so we'll draw it awfully first, is that we would end with something along these lines. Right? And we end up with a phosphorus oxide, which turns out to be a relatively stable species on its own, which is why it can break apart this way. And then we also end with an alkene. The instant we have an alkene, we need to be considering what the three-dimensional structure looks like. Some of you are probably sick of me mentioning that, but it's important when we go through to draw this. Okay? The hybridization of those carbons is sp2, which means we need to draw it in such a way that we are accurately representing the three-dimensional molecule. And that becomes important because when we draw that out, what we should now see is that we get these two large groups that are located on opposite sides of the double bond, meaning we have a trans configuration, okay, or an E configuration. This is really important because the mechanism is now telling us this. But wait, we said we don't know the exact process behind that mechanism. Okay? That exact mechanism is going back to those points being chiral atoms in that structure. But if I don't know how that formed, how do I know the final alignment of my double bond? That is a phenomenal question, and that's where the debate comes in, which means you don't need to know that. What you do need to know is that there is the potential for the other configuration. Okay, so when we're running the Wittig reaction, you're going to get a mixture of E and Z isomers. Okay, the exact balance of that mixture has a lot to do with the individual R groups that started the reaction off. Because you don't have the exact information there, you don't need to know that. What you do need to know is that both the E and the Z are potential products. Okay? Big deal here. We've now taken a carbonyl structure with an alkene, and we started with a carbonyl and an alkyl halide, and we've now combined them to make a larger structure, and we've maintained some chemistry in it. We have an alkene. That alkene now sets us up for all of those electrophilic addition reactions that we ran in our first review unit and potentially going all the way back to first semester. That's why this is neat. We get a larger structure and keep the chemistry. Cool. Okay, and that's one of the reasons why Wittig is a famous reaction. Okay, so we've got some practice questions here. See what you can come up with. Note they are formatted in slightly different fashions because there's varying ways at which you could see your Wittig reactions. I'm going to attempt to pause the video. Actually, no, I'm not. I'm just going to say, go ahead and pause. Solve. Did you solve? Cool. If you haven't solved, you should pause the video before you continue listening. So if we take a look at that first one, what's happening? We've got our standard alkyl halide. Note, there's our carbonyl. Note the little weird oddity here is that we drew it differently. Okay, that's a CH3 bonded to a carbon, bonded to a CH3 carbonyl. You're responsible for knowing how to do that. As soon as you draw that, this reaction should look really familiar because it's literally the one we just solved. Okay, so our PPH3 reacts with the alkyl halide, okay, to form our precursor to the ylide. The butyl lithium then comes in with that material, which makes us our ylide, which can then react with our carbonyl compound to set us up with our final answer. We've got the 4 carbons of our alkyl halide. Oh, it's not the exact same structure. There's our new pi bond connecting them, and then we have the ketone there. Okay. You can do a cheat, which you might be starting to notice. Draw your ketone, draw your alkyl halide aligned towards it, erase the middle out, connect them up, and you've now got your product. Guaranteed you're not going to see it drawn that way on an exam. Why? Well, not just because organic chemists are jerks, but that doesn't show kind of the proper chain length. And if we showed it that way, everybody would just jump all over the cheat. So if we count 1, 2, 3, 4, 5, we're looking at 5 carbons in a line. At position 2, we have a double bond, methyl, methyl. Do I need to be concerned about cis and trans in this one? No. These 2 methyls are indistinguishable, which means I don't have to worry about cis and trans. There's really only one product out of this one. Cool. So there we go. There's our final product. If we move to the next one down, you might be like, well, everything's changed. Yes and no. Okay. If we go through, first off, we're starting with the carbonyl, which was step 3 last time. You'll also note that we don't have 3 steps, but the first 2 steps up here were to make the ylide with the phosphorus connected. Ta-da! We're starting with the ylide now. Okay, so what we could do is draw our resonance with that, our PH3 phosphorus, CH2, CH3. There's our negative charge. The negative can now come in and attack, bust that open, do our goofy dance, and we would end with our final answer. Here's our phenyl. Remember, double bond out. This carbon is this carbon. That's the one that connected out. That becomes important because I need 3 carbons in a line. So 1, 2, 3. It is very common to lose carbons in this process. Watch out for that. Easy way to check that, count your carbons. So if we go through and look, I've got 3, 4, 5, 6, 7, 8, 9, 10. Of course, I didn't draw the double bonds. If we look at our starting, 1, 2, 3, plus 6 is 9, 10. So I've got the right number of carbons. Counting carbons can minimize that loss of carbons in your final answer. Last one becomes tricky because now what we want you to do is provide the two starting materials for this. Okay, so what we're looking at is how do we cleave that double bond. Okay, so first process I would recommend if doing this, stretch your double bond, erase the middle out of it, draw a carbonyl. Ta-da, carbonyl. The other half needed to be an alkyl halide. Okay. For those of you who looked at it and been like, well, couldn't you have done it the other way? Couldn't I have stretched that double bond, erased the middle out of it, and put a carbonyl here and the alkyl halide on the other side? Yes. That's why I asked for two methods. There were two ways that you could go through and do this. Hard question, which one's better? Okay. Recognizing the better is now going to go all the way back to did you understand and remember all of those pieces that we talked about through the mechanism. Step one is the clutch for this. Step one was an SN2 reaction. That SN2 is best with a primary halide. The blue path is correct. On a multiple choice exam, both of these answers will show up as possibilities. You need to acknowledge that the blue one is better because it's starting with that primary alkyl halide. It's a bit tricky, but I have full confidence in your abilities to be able to answer that. Okay. After that, we've got another one that I'll just kind of throw out there and let you kind of struggle through on your own. I won't actually provide you answers unless you ask for them. And I'm going to say unless you ask for them in our discussion board, Piazza, to help kind of process this. So you should be looking at two different methods for how you could go through and make these. Okay. The second one, I will argue, it says too different, whereas the top one says too Wittig. The second one, you don't have to do Wittig, okay, which is a big hint for how you could go through and solve that. And I believe with that, we've actually hit the tail end of this. Yep, we'll look at synthesis in the next video. So thanks for listening, and we will attempt to go ahead and stop this recording.